So let's take a look at this application. The percentage of a population which uses cell phones is described by the logistic DE. P prime is equal to P times 1 minus P, where T is measured in years. Initially, 10% of the population use cell phones, i.e. P of 0 equals 0.1. Solve the DE to find a formula which gives P of T for arbitrary times T. Note that P of T lies between 0 and 1. So let's write out the DE. We have P prime equals P times 1 minus P. And we have an initial condition, P of 0 is equal to 0.1. Just by looking at the DE, we can tell that it's nonlinear. If we distribute the P, we get P minus P squared, which is nonlinear. So let's use the separable technique, and I'll write this as dP dt is equal to P 1 minus P. And if I separate this out, I get dP over P times 1 minus P is equal to dt. And so now we're ready to integrate. And the right hand side is just simply T plus some arbitrary constant C. But on the left hand side, it seems like we're going to have to do a partial fraction decomposition. So let's see. Let's figure out what 1 over P times 1 minus P actually gives us. So I'm going to decompose that into A over P plus some B over 1 minus P and try to determine A and B. If I multiply both sides by P1 minus P, I get 1 is equal to A times 1 minus P plus BP, which also gives A minus AP plus BP, or 1 equals, so if I factor out a P, I get a B minus A times P plus A. So on this linear term, B minus A times P, well, there are 0 P's on the left hand side. So I could say B minus A is equal to 0. And the only constant, A, is equal to 1. And since A is equal to 1, I have B minus A is equal to 0. That means B must also equal to 1. So now we can go back and rewrite the left hand side here. I get the integral of A over P. Well, A is just 1. So I get 1 over P dP. So just write this dP over P plus B over 1 minus P. So it'll be plus the integral of dP over 1 minus P is equal to T plus C. Alright, so this is pretty straightforward. The integral of dP over P is just a natural log of the percentage, and of course it's always positive, so I'll just write this as the natural log of P. And here, if I let U equal to 1 minus P, then I get du equals, it's like a negative dP, or a negative du is equal to dP. So I get the integral of a negative du, where the negative can come out, so I get the integral of du over u, which is the natural log of u, so this becomes a minus the natural log of the magnitude of u. 1 minus P is equal to T plus C. And since P is always between 0 and 1, again, this 1 minus P term should always be positive. So I get the natural log of just the binomial 1 minus P. And since I have the subtraction, I use my properties of logs to write this as the natural log of P all over 1 minus P is equal to T plus C. Exponentiating both sides, I get P over 1 minus P equals e to the C times e to the T, which I'll just write as C1 e to the T. So now if I multiply both sides by 1 minus P, I'll get P is equal to C1 ET 1 minus P. And let's go ahead and apply the initial condition now. So I'll get 0.1 for P every time that T is 0. I should have applied it a little bit earlier. So here I get 0.1 equals C1, each of the 0 is 1, times 1 minus P, or 1 minus 0.1 is 0.9, which says that my C1 is 0.1 over 0.9, or 1/9. So let's continue. We can write this. Let's continue from this step here. So let's see. This will give me my P is equal to C1, that's a 9th, e to the t times 1 minus P. And if I distribute that, let's see, I get 1/9 e to the t minus a 9th e to the t times P. And let's transpose this term. So we'll bring it over to the other side. I'll get P plus 1/9 e to the t P is equal to 1/9 e to the t. If I factor out a P, I get 1 plus 1/9 e to the t is equal to 1/9 e to the t, which gives me my function P of t is equal to 1/9 e to the t all over 1 plus 1/9 e to the t. And I guess I can multiply the top and the bottom by 9, same as multiplying by 1, and I should get my percentage function, which is going to give me e to the t all over 9 plus e to the t.